Hello students, I hope you all are doing good. So today we are going to discuss NCERT section 13.1 to 13.3 and example 13.1 of chapter Nuclei. This is the disclaimer. Let's see strategy for competitive exams for the chapter Nuclei. Start by mastering the basic nuclear properties. You should focus on atomic number, which tells us the number of protons in a nucleus, and mass number, which is the total number of protons and neutrons. Understand the concept of mass defect and nuclear binding energy. The mass defect is the difference between mass of a nucleus and the sum of the masses of its individual protons and neutrons. We use Einstein's famous equation E equal to mc square, where E is energy and m is mass and c is the speed of light, to calculate this energy. You should learn how to calculate nuclear density. Nuclear density is the mass of the nucleus divided by its volume, and it's almost the same for all nuclei. You should explore nuclear fission and fusion. Fission is when a heavy nucleus splits into two lighter nuclei, and fusion is when two light nuclei combine to form a heavier nucleus. Notice how fusion generally releases more energy per nucleon than fission, and both processes have important real-life applications. At this point, it's important to practice solving problems. Try questions from past year JEE and NEET exams, which you can find at the provided websites. Finally, for further study, check our website for recommendation books and guidance. Let's start by looking at what you will be able to do after this lecture. Our focus is on the structure and properties of atomic nuclei, which are at the heart of every atom. You will be able to understand the basic structure and composition of atomic nuclei. We will define key terms, isotopes and isotones. We will also discuss nuclear density, which is extremely high, much greater than ordinary matter, showing how tightly packed nucleons are inside the nucleus. Next, we will learn about the atomic mass unit, which is a standard unit for measuring atomic and nuclear masses. We will cover the discovery of the neutron and see how the nuclear radius relates to the mass number. We will explore these relationships with examples to make the concept clear. Let's see the index of topics that we are going to discuss today. We will begin with a brief introduction to the topic. Let's see what specific areas we will cover in this chapter. Next, we will cover NCERT section 13.2, that is atomic masses and composition of the nucleus. And after that, we will discuss NCERT section 13.3, that is size of the nucleus. And at last, we will look at the example 13.1 to see how these ideas work in practice. So let's look at the objective. We want to understand what makes up the nucleus of an atom and what properties it has. The nucleus is a tiny but crucial part of every atom, and by the end of this lesson, you will know why it's so important. Now notice that most of an atom's mass and all of its positive charge are packed into the nucleus. This means that even though the nucleus is extremely small compared to the whole atom, it holds almost all the weight and the positive charge. This concentration of mass and charge is what gives the nucleus its unique properties. Nuclear symbols, atomic number, mass number, isotopes, and nuclear radius are used to describe a nucleus and its relationship between radius and mass number. Now let's focus on nuclear density. The density of nuclear matter is extremely high and stays nearly constant, no matter the size of the nucleus. This tells us that nuclei are incredibly compact, much denser than anything we encounter in everyday life. For example, nuclear density is about 2.3 times 10 to the power 7 kilograms per cubic meter, which is far greater than the density of the ordinary materials like water or metal. Now let's talk about mass defect and binding energy. The actual mass of the nucleus is always less than the total mass of all its protons and neutrons added together. This difference in mass is called the mass defect. The energy that corresponds to this missing mass is called the binding energy. We calculate it using Einstein's famous equation E equal to delta mc square, where E is energy, delta m is the mass defect, and c is the speed of light. For example, even a tiny mass defect can produce a huge amount of energy because c squared is such a large number. Next, look at nuclear reactions. Nuclei can change through reactions like fission and fusion. These processes are responsible for the energy in nuclear power plants and even in stars. Fission is when heavy nucleus splits into two or more smaller nuclei. For example, uranium-235 can split into barium and krypton, releasing energy and more neutrons. This is the principle behind the nuclear reactors and atomic bombs. Fusion is the opposite process. Here, two light nuclei like hydrogen isotopes combine to form a heavier nucleus, such as helium. This is the process that powers the sun and hydrogen bombs. Fusion releases even more energy per unit mass than fission. Both fission and fusion release large amounts of energy because some mass is converted into energy, as we saw with E equal to mc squared. Let's understand the concept of the atomic mass unit. This is a fundamental idea in nuclear physics and chemistry, as it helps us compare the masses of atoms and subatomic particles in a simpler way. Now let's define what an atomic mass unit or U actually is. One atomic mass unit is defined as 1/12 of the mass of carbon-12 atom. Carbon-12 is a specific isotope of carbon and it's used as the standard for atomic masses. Here is the formula for atomic mass unit. 1 U equals the mass of one carbon-12 atom divided by 12. This means if you take the mass of a single carbon-12 atom and split it into 12 equal parts, each part is one atomic mass unit. Let's put some number to this definition. The mass of one carbon-12 atom is about 1.992647 times 10 to the power minus 26 kilograms. So if we divide this value by 12, we get the mass of one atomic mass unit in kilograms. So after dividing, we find that one atomic mass unit is equal to 1.660539 times 10 to the power minus 27 kilograms. Mark this as 13.1 equation. Now let's look at the mass of the proton and neutron in atomic mass units. The mass of a proton is about 1.00727 U. This means a proton is just slightly heavier than one atomic mass unit. Similarly, the mass of a neutron is about 1.00866 U, which is just a bit heavier than a proton. Both of these values are very close to 1 U, but not exactly equal. This small difference is important in nuclear physics, especially when we discuss binding energy and mass defects. Isotopes are a key idea in nuclear physics and chemistry, and they help explain why atoms of the same element can behave differently in some situations. Let's start by defining exactly what isotopes are. So let's look at the definition of isotopes. Isotopes are nuclei of the same element that have the same atomic number, which we call Z, but different mass numbers, which we call A. Remember, the atomic number tells us how many protons are in the nucleus, while the mass number is the total number of protons and neutrons. Notice here that isotopes have the same number of protons, but a different number of neutrons. For example, if two atoms both have 6 protons, they are both carbon. But one has 6 neutrons and other has 7, they are different isotopes of carbon. Since isotopes have the same atomic number, they have identical chemical properties. This is because chemical reactions depend on the number of electrons, which is determined by the number of protons. So even though isotopes have different masses, they react the same way in the chemical reactions. Let's look at concrete example, the isotopes of hydrogen. Hydrogen has 3 common isotopes, hydrogen 1, hydrogen 2, hydrogen 3. Okay, each has 1 proton, but they have different number of neutrons, that is 0, 1 and 2 respectively. This shows how isotopes of different elements can have different mass numbers but same atomic numbers. Hydrogen 1 is also known as simply hydrogen, and hydrogen 2 is known as deuterium, and hydrogen 3 is known as tritium. To sum up, all hydrogen isotopes have same atomic number, which means they are all hydrogen, but their mass numbers are different because of their varying number of neutrons. Let's learn how to calculate the average atomic mass of chlorine using the abundances of its isotopes. First, let's look at chlorine itself. Chlorine has 2 main isotopes, which are atoms of the same element with different number of neutrons. The masses of these isotopes are 34.98 atomic mass units and 36.98 atomic mass units. Notice that these values are close to whole numbers and they are nearly multiples of the mass of a hydrogen atom, which is about 1 atomic mass unit. Now let's talk about the relative abundances of these isotopes. The first isotopes makes up 75.4% of all chlorine atoms, while the second isotope accounts for 24.6%. This means that in any sample of chlorine, about 3/4 of the atoms are the lighter isotope and about 1/4 of the sample is heavier isotope. To find the average atomic mass of chlorine, we use a weighted average. That means we multiply each isotope's mass by its percentage abundance, add the results and then divide by 100. So the calculation is atomic mass of chlorine atom equals 75.4 times 34.98 plus 24.6 times 36.98 divided by 100. When we do the calculation, we get an average atomic mass of 35.48 atomic mass units for chlorine. This matches the value you see on the periodic table. So the atomic mass of an element reflects both the masses and the abundances of its naturally occurring isotopes. Here our objective is to understand two important concepts in nuclear physics, isobar and isotones. These terms help us classify nuclei based on their number of protons, neutrons and total mass number. Let's examine what isobars are. Isobars are nuclei that have the same mass number, which we call A, but different atomic number, which we call Z. The mass number A is the total number of protons and neutrons in the nucleus, while the atomic number Z is just the number of protons. So isobars have the same total number of nucleons, but a different number of protons and neutrons. Notice this example, hydrogen 3 written as H31 and helium 3 that is written as helium 32. Both have a mass number of 3, but hydrogen 3 has 1 proton and helium 3 has 2 protons. Now let's move on to the isotones. Isotones are nuclei that have the same number of neutrons, which we call N, but different number of protons and mass numbers. This means that even though the elements are different, the number of neutrons inside their nuclei is exactly the same. For example, gold 197 written as AU 19779 and mercury 198 written as Hg 19880. Both have 118 neutrons. You can find the neutron number by subtracting the atomic number from the mass number, that is n equal to a minus z. So for gold 197, n equal to 197 minus 79, which is equal to 118. And for mercury 198, number of neutrons n equal to 198 minus 80, which is equal to 118 again. So remember that the nucleus of any atom is made up of protons and neutrons. These two particles determine whether nuclei are isobars, isotones, or something else. Now we are starting our study of the nucleus, focusing on what it's made of, protons and neutrons. Our main objective is to understand the basic composition of the nucleus, which is at the heart of every atom. Let's begin by looking at the proton, one of the two main particles found inside the nucleus. First, notice that proton carries a positive electric charge. The value of this charge is plus E, which is 1.602192 times 10 to the power minus 19 coulombs. The unit coulomb is the standard SI unit for electric charge. This positive charge is what makes protons interact with electrons and other charged particles. Now let's talk about the mass of the proton. The mass of a proton is 1.67262 times 10 to the power minus 27 kilograms. This is very small mass, but it's significant at the atomic scale. Now that we have covered the proton, let's move on to other key particle in the nucleus, that is the neutron. The neutron is the second main component of the nucleus, just like the proton. Unlike the proton, the neutron is electrically neutral. That means it has no electric charge. It's neither positive nor negative. The mass of the neutron is slightly higher than the proton. It is 1.67493 times 10 to the power minus 27 kg. One interesting fact that neutrons is that when they are free, meaning not inside a nucleus, they are unstable. A free neutron will decay into a proton and electron and an antineutrino with an average lifetime of 1000 seconds or roughly 17 minutes. However, inside most nuclei, neutrons are stable and help hold the nucleus together. Let's introduce a key term, nucleons. Nucleons is the collective name for the particles found inside the nucleus, which are protons and neutrons. Notice the diagram here. It shows the basic structure of an atom with the nucleus at the center containing those nucleons. Proton carries 1 unit of fundamental charge and is stable, and we know that the number of these electrons outside the nucleus of the atom is Z, the atomic number. If we add up the charges, the total charge from all the electrons is negative Z times E, that is minus ZE, where E is the elementary charge. Since atoms are neutral overall, the nucleus must have a total charge of plus ZE to balance out the charge of electrons. So the number of protons in the nucleus is exactly Z, which is the atomic number. This means the atomic number not only tells how many protons are in the nucleus, but also determines the identity of the element. Now let's look at how we symbolically represent a nucleus. We use a notation AXZ, where X is the chemical symbol of the element. Z, called the atomic number, tells about the number of protons in the nucleus. Remember, the number of protons determine which element it is on the periodic table, and Z is always a whole number with no units, and A is the mass number. Next we introduce N, which stands for neutron number. N is simply the number of neutrons in the nucleus. Neutrons are neutral particles, and together with protons they make up the mass of the nucleus. Both protons and neutrons are counted as individual particles, so N is also a whole number. Now let's define A, the mass number. A is total number of protons and neutrons in the nucleus, and A equals Z plus N. This means if you know the atomic number and the neutron number, you can always find the mass number by adding them together. To summarize, A represents the total number of protons and neutrons in the nucleus. So example, gold 19779 represents the gold nucleus, which has Z equal to 79 protons. Okay, so atomic number is 79. Mass number A is equal to 197. So total nucleons, so mass number represents the total nucleons, 197. So number of neutrons can be found. So N equal to mass number minus atomic number, A minus Z, which is equal to 197 minus 79, which is equal to 118 neutrons. Now let's see how the neutron was discovered by James Chadwick. So discovery of neutron was a major milestone in nuclear physics as it revealed the existence of a new neutral particle inside the nucleus. James Chadwick noticed something interesting when he bombarded beryllium nuclei with alpha particles. He observed that this process produced a type of radiation that had no electric charge. It was neutral. This was unusual because most known radiation at the time was either positively or negatively charged. So what was the reaction of the experiment of James Chadwick? That is, he bombarded the beryllium 94 nuclei with the alpha particle, that is helium nuclei. So He42. So this reaction gives carbon 12-6 plus 1 neutron. So Chadwick found that this neutral radiation could knock protons out of the light nuclei like helium, carbon and nitrogen. This means the neutral particles had enough energy and mass to physically dislodge protons, which suggested that they were not just ordinary light waves or photons. At that time, the only neutral radiation scientists knew about was electromagnetic radiation like photons. But photons don't have enough mass to knock off protons out of the nuclei. This observation made Chadwick suspect that neutral radiation was something different, something with mass. By applying the law of conservation of energy and momentum, Chadwick showed that these neutral particles had a mass almost equal to that of protons. This was the key evidence for the existence of the neutron. A neutral particle was with nearly the same mass as proton. This discovery completed our basic picture of atomic nucleus, which contains both protons and neutrons. Let's study the size of nucleus using the Rutherford model. Take a look at the diagram in the center. This shows Rutherford's famous alpha particle scattering experiment. Notice how alpha particles are directed at a thin gold foil and we observe how they scatter. Let's focus on what the experiments revealed when alpha particles with kinetic energy 5.5 mega electron volt, where mega electron volt is a unit of energy, were fired at the gold nucleus. The closest they could get was 4 times 10 to the power minus 14 meters. This distance is incredibly small and it tells us just how tiny the nucleus is compared to the whole atom. Next, let's see how Rutherford explained these results. He realized that the scattering of alpha particles could be understood if we assume that the only force acting was the Coulomb repulsive force. This is the force that pushes two positive charges apart. So as the positively charged alpha particle approaches the positively charged gold nucleus, it gets repelled, causing it to scatter. Finally, since all the positive charge is packed into the nucleus and the alpha particle can't get any closer than 4 times 10 to the power minus 14 meters, the actual size of the nucleus must be even smaller than this distance. This experiment gave us our final real estimate of how small the nucleus is compared to the atom. So our objective here to understand how the size of nucleus relates to its mass number, which we call A. The mass number is simply the total number of protons and neutrons in the nucleus. Let's look at what experiments have shown us. Rutherford's famous alpha particle scattering experiment revealed that the nucleus is extremely small compared to the atom, but its volume increases as we add more protons and neutrons. In fact, the volume of a nucleus is directly proportional to its mass number A. So as A increases, the nucleus gets bigger. Now let's connect this to the formula for the volume of sphere, which is V equal to 4 by 3 times pi times r cube, where r is radius of the nucleus. Since the volume is proportional to A, we can write 4 by 3 pi r cube proportional to A. This means that as we increase A, the radius r must also increase, but not in the simple one-to-one way. If we take the cube root on both sides of our proportionality, we find that r is proportional to a to the power 1/3 or r proportional to a raised to power 1 by 3. This means that if you increase the mass number by a factor of 8, the radius also doubles. So the nucleus gets bigger as you add more particles, but not as quickly as mass number increases. Now look at the relationship between the nuclear radius and the mass number of an atom. The objective here is to understand how the size of nucleus changes as we increase the number of nucleons or mass number A. Notice the graph shown here. This is the plot of nuclear radius versus mass number. Pay attention to the trend in the graph as we move forward. Now let's look at the mathematical formula that describes this relationship. R equal to R naught A raised to power 1 by 3. Here r is the radius of the nucleus and A is the mass number and R naught is the empirical constant. This formula tells us that as the mass number increases, the radius increases, but not linearly. It increases with the cube root of A, that is mass number. For example, if mass number increases by the factor of 8, the radius only doubles, since 8 raised to power 1 by 3 is equal to 2. Experimentally, the value of R naught is found to be 1.2 times 10 to the power minus 15 meters, which is also called 1.2 femtometers or 1.2 Fermi. Remember, 1 Fermi is equal to 10 to the power minus 15 meters. Now our objective here is to show that nuclear density is constant regardless of the size of the nucleus. First, let's define what we mean by nuclear density. Nuclear density refers to how much mass is packed into a given volume inside the nucleus. It's similar to how we think about the density of everyday objects. Now look at how we can derive the formula for nuclear density, which we usually represent with the Greek letter rho. Mass of a nucleus is approximately equal to the number of nucleons, A, multiplied by the average mass of single nucleon, M. Here M is about 1.67 times 10 to the power minus 27 kilograms, which is the mass of proton or neutron. Next, let's calculate the volume of the nucleus. The nucleus is roughly spherical, so its volume is 4/3 pi times the radius cube. The radius of the nucleus is given by R equal to R naught times A raised to power 1 by 3, where R naught is constant, about 1.2 times 10 to the power minus 15 meters. When we substitute this into the formula, volume formula, we get volume equals to 4 by 3 pi times R naught A raised to power 1 by 3 whole cube. And finally we get 4 by 3 pi R naught cube A. Now let's put this together to get the density formula. Density rho is simply mass divided by volume. So we take the mass we found earlier and divide it with the volume expression we just derived. When we substitute the expression for mass and volume, we get rho equals to m times A divided by 4 by 3 pi R naught times R naught cube times A. Notice that A represents the mass number, that is number of nucleons. So finally, after cancelling A from both numerator and denominator, we get rho equals to 3 times m divided by 4 times pi times R naught cube. This shows that nuclear density depends only on constants, the mass of a nucleon and constant R naught. So nuclear density is the same for all nuclei, no matter how big or small. So now let's look at the value we will use. The mass of nucleon, which is either a proton or a neutron, is about 1.67 times 10 to the power minus 27 kilograms. The typical radius constant for a nucleus R0 is 1.2 times 10 to the power minus 15 meters. Now let's set up the formula for nuclear density. Density, which we write as rho, is mass divided by volume. Our formula becomes rho equals to 3 times mass divided by 4 times pi times R0 cube. Here m is the mass of nucleon and R0 is the radius constant. Let's substitute the numbers into our formula. We have rho equals to 3 times 1.67 times 10 to the power minus 27 kilograms divided by 4 times 3.14 times 1.2 times 10 raised to power minus 15 meter cube. After calculating, we find that the nuclear density is approximately 2.3 times 10 to the power 10 to the power 17 kg per meter cube. This is extremely high density, much greater than anything we encounter in everyday life. This calculation shows us that nuclear density is constant and does not depend on the mass number A, which is total number of protons and neutrons in the nucleus. So to conclude, we have demonstrated that density is a characteristic property of all nuclei. It doesn't change with the size or type of nucleus. Let's examine the question. We are given the mass of an iron nucleus as 55.85 atomic mass units and its mass number A is 56. We are asked to find the nuclear density. Notice how this problem tests your understanding of nuclear structure and density. It combines concept of atomic mass, volume of a nucleus and density calculations. So first let's list out what information is given in the problem. So here we see that mass of the iron nucleus is given as 55.85 unified atomic mass units or U. Remember, U is a standard unit for atomic mass and nuclear masses, where 1 U is approximately the mass of 1 proton or neutron. Mass number is given as A equal to 56 and 1 U is equal to 1.66 into 10 to the power minus 27 kg. Let's restate the mass of the iron nucleus as MFE equals 55.85 U. Now let's convert the mass from atomic mass units to kilograms. We multiply 55.85 by 1.6605 times 10 to the power minus 27 kg, which gives us approximately 9.274 times 10 to the power minus 26 kg. Alternatively, we can estimate the mass by multiplying the mass number A, which is 56, by the mass of a single proton, about 1.67 times 10 to the power minus 27 kilograms. This gives us another way to check our calculation and understand how the total mass is built up from individual nucleons. First, let's find the radius of the nucleus. The formula we use R equal to R0 A raised to power 1 by 3, where R0 is a constant, about 1.2 times 10 to the power minus 15 meters, and A is the mass number. This formula tells us that the number of nucleons increases, the radius grows, but not linearly. It's proportional to the cube root of A. Let's substitute the values into the formula. We have R equal to 1.2 times 10 to the power minus 15 meters multiplied by 56 raised to the power 1 by 3. Here 56 is the mass number for iron and we are raising it to 1/3 power to find how much bigger the nucleus is compared to single nucleon. Calculating further, 56 to the power 1/3 is about 3.82. So multiplying this by 1.2 times 10 to the power minus 15 meter give us R equal to 1.2 times 10 to the power minus 15 meters times 3.82. After multiplying, we get the radius R equals to 4.584 times 10 to the power minus 15 meters. This is the estimated radius of an iron nucleus. Notice how small this value is. Let's write down the formula for the nuclear density. Density, which we use the Greek letter rho for, is mass divided by volume. For a nucleus, the volume is that of a sphere, so it's 4 by 3 times pi times the radius cubed. Here m is the mass of the nucleus in kilograms and r is its radius. Now let's substitute the values into our formula. This mass, the mass is 56 times 1.6 times 10 to the power minus 27 kg upon 4 by 3 times pi times 4 by 4.584 times 10 to the power minus 15 meter cube. After calculating, we get the numerator as 9.352 times 10 to the power minus 26 kg upon 4.04 times 10 to the power minus 43 meter cube. So finally, dividing the mass by volume, we find the nuclear density is approximately 2.3 times 10 to the power 17 kilograms per cubic meter. This is an incredible high density, much greater than anything we encounter in everyday life. So let's summarize the topics that we have covered today. Start by defining the atomic mass unit, or U. One atomic mass unit is exactly 1/12 of the mass of carbon-12 atom. This unit helps us compare the masses of atom easily, since atoms are so small that using kilograms would be impractical. Isotopes are atoms of the same element, so they have the same number of protons, but they have different number of neutrons, which means their mass numbers are different. Isobars are atoms that have the same mass number, which means the total number of protons and neutrons is the same, but they have different atomic numbers, so they are different elements. Isotones are nuclei that have the same number of neutrons, even if their number of protons and mass numbers are different. The nucleus is made up of protons, which are positively charged, and neutrons, which have no charge. Together, these particles are called nucleons. Understanding the composition of the nucleus is essential for studying nuclear reactions and properties. The atomic number, written as Z, is simply the number of protons in the nucleus. The mass number A is the total number of nucleons, which means protons plus neutrons. So the formula A equal to Z plus N tells us that the mass number equals the number of protons plus the number of neutrons. In 1932, James Chadwick discovered the neutron by bombarding beryllium with alpha particles. This experiment showed that there was a neutral particles in the nucleus, which we now call the neutron. Next, let's look at the size of the nucleus. The nuclear radius r is proportional to the cube root of the mass number A. The formula is r equal to r naught a raised to power 1 by 3, where r naught is a constant, usually about 1.2 femtometers. Nuclear density is approximately 2.3 times 10 to the power 17 kg per cubic meter, and it's nearly the same for all nuclei regardless of their mass numbers. So let's see the first question. If a nucleus has 82 protons and 126 neutrons, find mass number A. This is the fundamental concept in understanding how nuclei are described. Now let's calculate the radius of an aluminium 27 nucleus. The formula we use is r equal to r naught a raised to power 1 by 3, where r naught is constant, which is 1.2 femtometers, and a is the mass number. Next, let's find out how many neutrons are in uranium-238. Remember, the number of neutrons is simply the mass number minus the atomic number. Now consider two nuclei that have the same number of neutrons and equal to 50 but different atomic numbers. What are these nuclei of different elements called? Finally, let's convert two atomic mass units to kilograms. We use the relation 1U equal to 1.660539 times 10 to the power minus 27 kilograms. So this is all about today's lecture. I hope you enjoyed the session. Thank you for your attention.